I am Ashish Aggarwal as industry process consultant within CATIA, supporting.
Hello everyone, my name is Yuan. I'm an industry solution consultant with Simula brand of North America.
Thank you for joining this session on MODSIM Workflow for conceptual design of ROPS. Before we jump onto the workflow itself, I would like to highlight why we need this workflow and how it can impact conceptual design engineering of a product. Now, in today's product development scenario, design and simulation are significantly siloed. In addition, there is no to little simulation in conceptual phase. It is so because CAD and CAE have different tool environments. In most cases, simulation comes only after detailed design in CAD. It is even harder to bring simulation in concept drafting stage, where no 3D geometry exists. With modeling and simulation workflow that we will talk about today, we are fundamentally trying to show how we can bridge the gap between design and simulation, especially in conceptual phase, and let CAE drive the design, or function of a product drive its form. We call it experiential engineering as it lets you do full exploration of design space in a very short time. Before one can pick the best design, which is functionally validated by science and meets all other criterias like say packaging, styling. By driving design scientifically right from the conceptual stage itself, we can significantly improve KPIs like reduce time investment, do early detection of issues, which will save cost, and also come up with an innovative and improved quality of a product. To demonstrate this workflow, we have used excavator cabin structure as an example, and ROP simulation is driving the design. ROPS analysis consists of applying load to the structure of a cabin of an excavator. It can be applied on a tractor or earth moving machine, and so on. What we see here is a MODSIM workflow using tools from Dassault Systemes, CATIA, and Simulia brand to predict and optimize the design of an excavator cabin. So we started off with new release theme for cabin design of an excavator. There can be multiple inputs that drive this theme design. Now, once we have this theme design, it is structural engineers' responsibility to come up with an architecture to fit into this theme, which is comfortable and safe for an operator, at the same time, cost effective. In order to execute this in the most effective way, is to have 3D geometry, which can not only be simulated for real world scenarios, but allows users to perform trade off studies right in the conceptual phase, which are all scientifically driven. To do so, we use a unique tool within CATIA's portfolio called SFE Concept. Now, those of you who are not familiar with this tool, it is an implicitly parametric geometry tool which creates ready to simulate models by using an inbuilt measure. To create geometry in this tool, we start with points and lines, followed by extruding a section along this line to create surfaces. Here, geometry is at mid-surface and it's very light in nature. As we continue creating additional components, we simultaneously map to create a robust and parametric connection. Here, mapping is a projection of one object to another. Once we have the geometry which captures all functional details important for structure performance, we can assign properties to the surface which is required for simulation. We define thickness, material properties, and also welding on the geometry itself. We can use inbuilt measure to mesh the model, and this is like an associated mesh which is available all the time as long as surface geometry exists. Leveraging parametric ability of this tool, we could record design changes to set up DOE to study sensitivity analysis of shape and section change on overall performance of the structure. Therefore, we recorded global changes like varying the length of the cabin, varying section of the outer door ring, and also local changes like varying the position of rear cross member and varying the gusset size. CATIA SFE creates simulation-ready models for each design, which allows to run DOE study in batch mode at conceptual stage itself. To set this geometry up for ROP simulation, we have to define a rigid plate on top of the structure, constrained on the bottom in the same tuned environment. This iterative process is repeated over and over again in batch mode, where eyesight drives the DOE.
Okay, cool. So CATIA SFE created run-ready finite element and make the analysis life much easier. The main purpose of the ROP structure is to protect the operators of heavy equipment from injury and rollover incidents. In this analysis, Abacus explicit solver is used to simulate the cabin structure crushed by a rigid plate on the top. By doing this, we can get the force and displacement relationship curve and determine the maximum force the structure is able to withstand and correspondingly absorb energy. These engineering specifications are regulated by ISO standards and SAE standards, which must be satisfied. After we validate the single analysis works fine, we can get our baseline design KPIs with a maximum force, absorb energy, and corresponding mass. However, usually the baseline design is far away from our target KPIs. So in order to achieve our target KPIs, with minimum mass addition, we initiated a methodology to do shape and section optimization leveraging integrated MODSIM workflow through iSight. So iSight DOE component generates a design matrix and drives geometry updates in SFE concept component. An SFE concept component will automatically in batch mode to update shape and section dimensions to generate Abacus run-ready models. Then all the simulation required data will be fed into Abacus component for further analysis. The analysis can run on the laptop and also can scale up computer resources by connecting to HPC cluster to accelerate the analysis process. For example, we run the analysis on HPC cluster with 16 cores for each design, and it can finish within 30 to 45 minutes. And of course, we can add more cores to get the results much faster. For each design, the maximum force and absorb energy can be extracted and calculated, which will flow back into DOE component again for post-processing or result analysis. In the runtime gateway of iSight from Pareto plot, we can identify the parameter sensitivity to determine which parameter contribute most to the engineering specifications. For example, in this case, the door ring section contribute most to the maximum force, and also we are able to rank the design iterations based on the output responses and provide the design recommendation accordingly to the next step for detailed design.
So following this process, we can come up with a design which is fundamentally validated by science, and then feed it to CAD for detailed designing, which would be more like a manufacturable design. So when I say manufacturable design in concept stage, using this process flow, we capture all the functional details and validate the functional aspect of the design. So this workflow helps to identify the right direction. So by identifying key enablers to meet functional objectives, and this can be done by setting up a DOE very early in the stage to determine the best performing design with lowest weight. This can be done by applying enablers that improve the design. Specifically for this workflow, target KPIs were achieved without any significant weight compromise compared to just cage optimization on the baseline model. At this time, we would open it up for any questions. You can comment on the post if you have any questions. Even if you have questions after this session, you can comment on the post, and we'll be happy to answer all the questions you have. Thank you for listening to us, and have a good day.
Thank you, everyone. Have a good day.